Hey folks, today we're going to talk about torque, uh, not dork, but torque. So let me make an analogy, an actual analogy. So Newton's second law, force equals ma. So m is an object's resistance to changes in motion, aka resistance to acceleration. Okay, force causes an acceleration. Okay. Well, in a rotational system, instead of mass, we have moment of inertia I. So in a rotational system, I is resistance to angular acceleration or changes in rotational speed. So in a linear system, force makes things accelerate linearly. Well, what is it in an angular system that makes things angularly accelerate? Well, that thing is torque. Okay. And I will start right away with the equation for torque. Torque is R cross F. Okay. Now, cross product. That's how perpendicular two vectors are to each other. So if two vectors are perfectly perpendicular like this, okay, then they have the maximum cross product, and you would literally just multiply their magnitudes together. If the vectors go like this or like this, they have no part of one is perpendicular to the other, so those cross products would be zero. And then of course you might have something in between like this or like this. So one vector has part of it perpendicular to the other. Now, what trig function is a 0 at 0 degrees, is maximum at 90 degrees, and 0 at 180? Well, that trig function is sine, okay? So the magnitude of the torque is going to equal the radius times the force, the magnitudes of those, times sine of the angle between them. Now, they give us a phi here. I don't know exactly why they choose to use that for the angle in this case, but that's what I typically see in textbooks and such, so I'll use it. All right, units. Radius is meters and force is newtons. So torque is a Newton meter. Now, the other unit that Newton meters is joules. So you got to be careful here. For joules, for work, you do R or dot F. You multiply how parallel they are. So what you're doing with the newtons and meters is different for work. For torque, you're seeing how perpendicular they are, and so you get something called Newton meters, and there is no shortcut or no uh, shortcut unit for that. It's just Newton meters. Okay. Now, when you're calculating torque, and again, torque is what makes things angularly accelerate or tries to make things angularly accelerate, aka it tries to make things spin, okay, or stop spinning for that matter. When you're calculating torque, there's two ways to do it. You have to find how perpendicular one vector is to the other. So let me draw an example. Okay, let's say I've got a rod. Okay, and let's say it's pivoted at its end. So there's where you're spinning it about that point. Okay, so you're spinning it either clockwise or counterclockwise. And let's say you apply a force here, okay, at that point, okay, and in a direction that's not perpendicular to the rod. And just for the sake of argument, let's say this is x, okay? So there's two ways to figure out what the torque created by that force is, okay? So you can either determine how much of the force is perpendicular to x, okay? So in other words, we draw x. So here's your r, and there's your f. This is your r, and there's your f. This is your phi. That's your angle between them. And so you would just do r times, well, if you think about it, what component of f is perpendicular to r? Well, this little green component I just drew. How would you calculate that little green component of the force? Well, you do F sine phi, right? So in this case, you're doing R times F sine phi. Okay, and that would give you the torque created by that force, how much is trying to make that bar spin. Okay, but the other way to do this is to try to find how much of X is perpendicular to the force. Okay, we call this has a name. It's called the perpendicular lever arm. Okay, and I've probably spelled perpendicular wrong, but hey, I'm not a speller. So perpendicular lever arm. Okay, so the perpendicular lever arm just means this. Okay, imagine you have that force up there, and imagine it's part of a line that's an infinite line. So let's make an infinite line that includes that force. It keeps going forever. Okay, what is the shortest distance from our axis to that line? All right. Well, that shortest distance would be this perpendicular distance right there. Okay. That is the perpendicular lever arm. That's the shortest distance from our axis to the line of force. Okay. So if you were calculating torque this way, you would take the force, okay, so it'd just be F times that distance. What's that distance? Well, if you look at this little right triangle here, here's phi, and that's the opposite leg of a right triangle. So it's times r sine phi. So you'll notice that either way that you calculate the torque, you get the same answer, just a different order in the way you calculate it. So different problems lend themselves to one or the other method of determining the torque. It literally just depends on the problem and the things that they give you. So in some instances, you'll see me use this first version where I'll find the force that's perpendicular to the lever arm. In some instances, though, you'll see me use the perpendicular lever arm. How much of the radius is perpendicular to that line of force? Okay. Now, let me give you an example of when the latter would be much more preferable. So let's say you have a door. Here's your door. And let's say it's hanging on one hinge, like, something's broken and there's just one hinge left on it. Okay. And I asked you for what's the torque of the door about that hinge. The door's trying to spin clockwise, right? If you imagine you put your hand here and you're trying to hold this hinge, the door's trying to spin clockwise, right? So what torque is that creating? Well, the force is the mass times gravity, the weight of the door at its center. So here is the weight of the door. That's what's causing the torque. That's trying to make it spin clockwise. Well, what if you wanted to try to do this first method? Okay, what you would have to know is you would have to know what's the distance from here to here. Okay, and then you'd have to figure out this angle. Okay, and then you would do sine of that angle to get how much of the weight is perpendicular to that radius. And if I gave those dimensions, you can do that. But holy moly, in this example, there's such easier way. All right, here's my axis. What's the shortest distance from the axis to the line of force? Well, hello, it's just half the width of the door. All right, so your what's called the width of the door, I don't want to call it W because I've already used that. Let's just call it D. So that's the width of the door. So the torque in this case would simply be D over 2 times the weight of the door. No angles necessary, none of that stuff. You just know that this distance here is half the width of the door, and you just plug it in. All right. So that's one example of the easiness of using perpendicular lever arm in certain situations. It's a lot easier than using the first method. Now, again, it's a 50-50 shot. Some problems lend yourself to this method. Some problems lend themselves to this method. So one of your jobs is to figure out which one is easier for me. Now, one last thing I'll leave you with, okay? In a linear system, we have net force equals ma, okay? Well, there's an analogous equation in an angular system. Instead of force, we have torque. Instead of mass, we have moment of inertia, and instead of A, we have alpha. Okay, so we have almost a perfect analogy here. In a linear system, you have x, you have velocity, you have acceleration, you have mass, and you have force so far. In an angular system, you have theta, you have omega, you have alpha, but now we have moment of inertia and we have torque. Okay, so any equation that you would use these, there's going to be an analogous equation where you just replace them with these. And that basically works every time. All right. Now, one last thing, and I'll probably start the examples with this too. Torque is a vector. And I will mention this now. let's say there's a radius this way. Let's say here's your pivot. Let's say it's a bar or something like that, and there's a radius, right? And let's say you apply a force down. So there's your R and there's your F, okay? For a cross product, the answer, the direction, you notice that this is a vector equation. You're taking two vectors and you're getting a vector out of it, okay? That vector has a direction, okay? For torque, here's how it works, okay? Imagine you put your pencil down for a second and you stick your right hand into the direction of the radius. So your hand will be pointing to the right. And then you curl your fingers down toward the direction of the force, okay? And then you stick your thumb out like a hitchhiker. If you do that, your thumb should point into the page right now, all right? The direction of the torque, okay, is into page. Now, we're going to talk more about this kind of direction stuff a lot more next semester, but I wanted to bring it up now. So torque is a vector. It has a direction. And in this case, for this example, it points into the page. For us, for now, it might be easier to think of it spinning as a clockwise or counterclockwise torque. Okay, looking at the page, which way is that force trying to make the thing spin, clockwise or counterclockwise? But a clockwise torque, its direction is into page. Okay, or another way to think about it, if you try that with your hand again, if you stick your hand to the right, curl your fingers down, and your thumb points into the page, you can imagine you're watching your right hand rotate around your thumb. That's the direction of the torque. So that thumb is kind of like the top of a top, and your hand is spinning around your thumb. That's the direction of the torque, is which way your thumb is going, and the spin is what it's causing around your thumb. We will talk a lot more about right hand. That's called right hand rule. You have to use your right hand, by the way. We will talk a lot more about that over time. For now, though, I just wanted to introduce it. For us, we can talk about clockwise and counterclockwise for the rest of the problems that we're going to do. The next video, I'll have several examples for you. I hope that was helpful, and thank you very much.